Hello class. In the previous lecture we have seen what is a work, okay, what is a thermodynamic work and what is a mechanical work. Now we will see why we are calling work as a path function, okay. So for that, now consider this is a process which I have shown on the slide. The process are carried forward in between a two state, that is state 1 and state 2. So here I have shown the process are done by three way. Okay, either it may done by this path, either it may done by this path, or either it may done by this path. Don't focus on the directional arrow. Okay, we are right now only performing the process from 1 to 2. We are not going back 2 to 1. So only consider 1 to 2, the arrow which is going from state 1 to state 2. Now if I want to calculate the uh, work done during the process the work done during the process by this path or by this path or by this path. So I have to calculate the shaded area present beyond below that curve. Okay, I have to calculate the shaded area present below that curve. So it is a one thing, it is a thing we have to do because here in state 1 and state 2, if you think the temperature and volume respect to that those states are remain same. For example, at state 1, if I check a pressure, then it will be a P1. Okay, if I check a volume with respect to state 1, that then it will be a V1. If I check the pressure with respect to state 2, it will be a P2. And when I look for the volume with respect to state 2, it will be a V2. So at the end point 1 and 2, the P1 V1 is same, the P2 V2 is same for all the three available paths. It's not like that from path 1 the value of P1 V1 is different, the value of P2 V2 is different. For this also, for all these three paths, the P1 V1 and P2 V2, those value are same. Okay, but then also if I'm going by path this one, then work done is different. If I'm going by the path this one, the work done is different, and if I'm going by this path, then work done will be different. So now we'll check how it possible. So first of all, I want to calculate a work done by the process during what or while traveling through path which is present at the center. So if I want to calculate the area of that shaded area of that process, then I supposed to draw such a what we can say a guideline or a lines which we supposed to guide us in order to represent a shaded area below that. So this area which is look like a trapezoid right now. Okay, okay, so whatever the area present below that line, this the shaded area, okay, that will be represent a work done by a process 1 to 2 by following this path. Okay, if I want to calculate it, then it will be like W equal to, again I have to do one thing, we will divide that area into two halves. Let's divide it. Okay, and if I name it, if I name it, if this is a 1A, if this is a 1B, if this is a 2A, then we will calculate the work done by this process. Algebraically, we are supposed to calculate. Okay, so A for area, area of right angle triangle 1 1 dash 1A dash 2 plus area of square or rectangle 1A dash 1B dash 2A dash 2. Okay, so this will be a work done by the process whenever system changes from state 1 to state 2. Okay, that is area, shaded area below that line. Okay, now will tell me, now will ask me how the shaded area will become a work done. Now if you look into a formula, if you look into the unit of work, okay, then here whenever I am calculating the shaded area, it is nothing but I am doing work is equal to pressure into volume. And if you look into unit of pressure, the unit of pressure is Newton per meter square. I am supposed to multiply Newton per meter square by volume, that is meter cube. So whenever I am multiplying the unit, I am getting here Newton meter, which is nothing but what? Joule. Okay, so by multiplying pressure into volume or calculating the area, shaded area on the PV plot, we are supposed to get a work done during that process. So whatever the shaded area present below the line 1 to 2, that is center process line 1 to 2, okay, it will give me a work done. Okay, so this is a thing with the center path, the path present at the center. If I look for the path which is going this way, or if I'm looking for the work done performed by this process, then definitely that much area will get added here. Okay, so work done will be more. If I'm look for the process followed by this path, okay, that below path, then what happened? Then the area, shaded area, will become less, then work done is less. Okay, so in that way, as I'm changing the path or in between the state 1 to 2 in order to transform the system, then the shaded area below that line, okay, will increase or decrease with respect to your system. Okay, or with respect to your path, with respect to the path followed by system. So that's why our work and heat are both are a path function, rather than a point function. So here we can say a work and heat are both are a path function, which is depend on the path. Now we will see a different type of works. Basically there are two types of work done are there. One is the reversible work done and second is the irreversible work done. Okay, so the reversible work done and irreversible work done is depend on the process. Okay, whether that work done is occur due to a reversible process or irreversible process. If that particular work done is occur due to reverse by following a path of reversible process, then such a work done is called as a reversible work done. And if if particular work done is occur due to a path of irreversible process, if particular work done is occur due to by following a path of irreversible process. In the previous slide we have seen a different path, this path. Okay, so if this path is reversible, okay, then we can say, if this path is reversible, then we can say the process is the process is reversible and the work done due to that process is reversible work done. If this path is irreversible, if this process is reversible, then it is called as a work done due to this irreversible process is irreversible work done. Similarly, the same way, the reversible and irreversible work done is there. Okay, reversible and the irreversible work done is there. So uh, the process said to be reversible when system changes. Now what, how we can say a process is reversible or irreversible? So it is said to be reversible when system changes its state 1 to 2. Okay, when system changes its state 1 to 2 and come back to state 2 to state 1 by without changing any property of system and surrounding. Means system 1 are shifting to state system are changing the state from state 1 to state 2. Okay, and it come back state 2 to state 1, but whenever it come back to state 1, that time the pressure, temperature, volume and the other characteristic of surrounding and system will regain as it was present during a system and surrounding at state 1. Means whenever system are transforming state 1 to state 2, okay, pressure, temperature, volume, other properties are changing definitely, but when it come back to state 1 from state 2 to state 1, then whatever the property changes, it again reappear as it is as they was previously at state 1. Okay, so such a type of process is called as a reversible process. If such a process is occur, then such a process is called as a reversible process. If it is not like that, then thus such a process is called as a irreversible process. Now there are two type of reversibility. One is the internal reversibility, another is the external reversibility. So what are the factor which responsible to make system irreversible, such as a friction? If this piston and cylinder pair will not have a friction in between them, then internally the process of expansion and compression of or process of piston movement up and down will be reversible. If there is no free expansion, if hysteresis or eddy current losses is not there, then we can say a system is internally reversible. And when externally reversible, if a system and surrounding will not have a finite temperature difference. For example, a system present at 10 degrees Celsius and surrounding present at 50 degrees Celsius, so there is a finite amount of temperature difference in between them, so heat transfer take place across the boundary. If it is insulated, then will not take. If boundary is insulated, then temperature, whether there is a temperature difference, then also there is a no chance of heat exchange. So we can say a system is externally reversible also. Okay, so uh, when we can say the system is externally reversible, whenever when we can say it is externally reversible whenever there is a no exchange of heat in between system and surrounding. And when exchange of heat in between system and surrounding are take place whenever there is a temperature difference in between them. Okay, and if temperature difference is also there. In that circumstances, if our boundary is insulated, then we can restrict the heat transfer in between system and surrounding. So two things you have to remember: system may be externally irreversible only when a boundary is insulated, or if there is a very negligible temperature difference is present in between system and surrounding. For example, system is present at 10 degrees Celsius and surrounding is present at 9.99 degrees Celsius. It means there is a very infinitesimal difference, very negligible temperature difference is present in between system and surroundings. So in that case, we can say system is externally reversible. Now, we will see the example of reversible process. Consider this is a piston cylinder assembly. Okay, so in this piston cylinder assembly, on that piston, number of weights are put it. Okay, and this piston is completely weightless and the piston is completely frictionless. This vessel is completely insulated from the surrounding. So I obey all the rule of internal and external reversibility. What is the rule of internal reversibility? There should not be friction. Okay, there not be a free expansion and no eddy current losses. So no any current factor we are considering here. So eddy current losses, no chance of eddy current losses over here. Now for the mechanical term, friction is not there. This is not there is no any friction is there and no free expansion. So here I am considering this piston is completely weightless and the frictionless. I am just adding a weight over the piston. Okay, and this for external irreversibility I am considering this vessel is completely insulated, or we can say there is a negligible temperature difference in between system and surrounding, as I told you 10 and 9.99. So sake of time, just consider it is completely insulated. Okay, instead of considering finite temperature infinite temperature difference. Okay, so the system is completely insulated, so again no temperature sharing heat sharing in between system and surrounding, so it is in externally also reversible. If I'm if I'm adding some additional weight on the piston over the piston slowly, then this thing supposed to move from state 1 to state 2. So as gas pressure P is present, okay, and I'm adding very slowly small weight on the piston, then what will happen? The pressure P goes on built up as piston moving downward direction, and as the process is very slow, the temperature generated inside the system is will not be rise will not be that much. Okay, is not that much, as because process is very slowly, as I am adding very slow weight on it. Okay, so pressure will not that much the develop inside the system is not that much, and even our piston and cylinder assembly are frictionless. So whatever the weight I am putting over here, the effect of that weight are completely converted into a work done. Okay, so as a piston is completely frictionless, so whatever weight I am here adding in order to push the piston in downward direction, that effect of weight are not used to overcome the friction in between piston and cylinder. It is directly utilized to push the piston downward. Okay, and only pressure P will give you a resistant force, not the piston cylinder friction losses. Okay, so that's why I'm said this thing is completely frictionless, because if there is a friction, then whatever the weight I am putting and effect of that weight is get absorbed by that friction also. That friction also may resist the movement of piston downward. So that's why we are saying it is a frictionless. Now if say whatever the weight I have added when the piston is uh, reaches to state 2, okay, and now I want to move back that piston again to state 1, that time what I have to do, I have to remove one by one the same way whatever weight I have added over it. So I start removing weight from the piston. Now my piston is supposed to move in upward direction slowly, and as there is a frictionless, so how much amount of work I have taken from the surrounding, the equal amount of work my system will giving back to the surrounding, because all the work which I have done on the system, okay, all the work I have done on the system will not get absorbed by friction. It is only utilized to compress the gas. And as gas expanding, all the work done is given back to the surrounding. So whenever piston reaches to state 1, uh, at in the, after it coming back to the state 1, all the properties of the system and the surrounding will remain same. So instead of here adding and putting the weight, if I make a different arrangement, okay, so the system will become a purely reversible. And in the true sense, the no such a system or exists in the world which is a completely reversible. That thing you have to note down. There is a no any system present in the world which is a completely reversible process. There is a friction, there is a hysteresis losses, there is a heat transfer in the small amount. Okay, so no process is reversible completely. Okay, now we will see the example of irreversible process. When we can say the process is irreversible, okay, this is the example, and almost all process exist in the world are irreversible. So I have just quoted over here one of the example from them. Okay, so now consider this is a vessel which is present over here, and it get separated by two compartment. At the center it having a piston. Again, if we consider it as a friction, then also it doesn't mean, okay, it doesn't mean it is a reversible. Okay, just consider now, as we have considered here, the piston is frictionless completely and weightless completely, and it have those stopper. So whenever I am removing those stopper, okay, what will happen, as I seen in previous lecture, this gas is responsible, the pressure of this gas is responsible to push that piston in this direction. Okay, as here vacuum is present, now my system transform from state 1 to state 2, is it? Now we will mark here, just for simplicity we will mark over here. So if this is a line of state 1, if this is a line of state 1, and if this is a line of state 2, if my piston it move from this way, this state to this state, okay, as soon as I have removed the stopper, okay, so it is a what kind of work? It is a free work, as we have seen. Okay, whatever the work done is there, it is a free work, as my system transform from state 1 to state 2. Now I want to come back from state 2 to state 1. What I have to do? I have to push the piston in this direction. Okay, and who will push the piston in this direction? I have to take a work from surrounding. Okay, either by mean of human effort, or either mean by other machine effort, or either mean by animal effort. Okay, I have to push a piston in this direction, means I have taking and borrowing the work from surrounding to system to push back that system or that piston from state 2 to state 1 to come back to initial state. Okay, and during that time what will happen, surrounding or start to lose a work. Okay, surrounding will start to lose a work, surrounding will start to lose a work, and that work will be W minus. Okay, that work will be a W, which is losses by surrounding. What happening exactly? The system borrowing the work from surrounding to push that piston. It's a initial state, so I am borrowing a work from surrounding, so surrounding losses of work and adding on the system. So here what will happen, system will reach to initial state, the pressure of the system will reach to initial state, the temperature of system will reach to initial state. But what with the surrounding losses the work. So whether surrounding reaches to initial state, no, surrounding not reaches to initial state, so that is a irreversible process. In addition to that, if I consider a friction between this piston and the cylinder, then a force whatever I have applied here to push back piston from state to state 1, that magnitude will be more. If without friction I am applying a 10 kilonewton of force to push that piston in initial state, when there is a friction, then I have to use a 20 kilonewton force, or out of that 10 kilonewton, 20 kilonewton get wasted to overcome the frictional losses in between piston and cylinder assembly. Okay, so this is the irreversible process, because whenever system come back to state 2 to state 1, we have borrowing the work from the surrounding, and that due to that, whenever system reaches to initial state, a system and surrounding not at a initial state. System is initial state but surrounding are not initial state, because it given that it loses the work. So both the system and surrounding need to be at initial state to have a process reversible completely. So there will be a chances system may be internally reversible but may not be externally reversible, or system may be externally reversible but may not be a internal reversible. So in that way, the no system exists in the world are totally reversible. If system are internally reversible and externally reversible both, then such a system is called as a totally reversible system. But in the universe, no system are totally reversible. So here I hope you have understood what is the concept of reversibility. If you feel any difficulty, do comment in comment section. Thank you.